Okay, this is Mr. Land speaking, and we are going to look at some math together today. Let's go pull that up there, make that as big as possible while we still have our calculator visible. Okay, so let's get started. Today's lesson is going to be involving triangles, and specifically 4 different topics that include triangles in them. Pythagorean's theorem, slope, y-intercept, and then we'll look at a little bit of dilations and transformations there at the bottom. Okay, so I'm going to try to do this where we do one section on the left. I'm going to just kind of show you by hand what we can do kind of using minimal calculator, and then our second example on the right for these, I'll go ahead and use our shortcuts that we learned in Desmos this year. So starting with Pythagorean theorem, which is exclusively dealing with triangles, I always recommend, if you don't know anything about Pythagoras the man, that you go and look him up sometime. He's a really interesting guy, and this is just such a small part of what he left us to study and to learn about. So starting with, what is the length of AC? So AC is the diagonal of this right triangle. And this theorem, as we've learned, it only works with right triangles, okay? And no, there are no such thing as left triangles. I have been asked that before. Right? It only works with right triangles. That means they'll have this 90-degree angle, right? Where there are 2 shorter sides, of course, and then the longer side, these are the legs, and the longer side known as the hypotenuse. Now, what I want to point out is that on our grid, right, it may be tempting to say, I'll just count, I'll just estimate, how long. You can't count in a diagonal fashion on this, and you can actually use Pythagorean's theorem to prove that, right? Very briefly, if Pythagorean's theorem, right, states that a squared plus b squared equals c squared, we know these are 1, right, and that the legs of the right triangle are shorter than the hypotenuse, then the diagonal distance this right triangle makes has to be greater than 1. So this is not one space, right? It's going to be 1 point. It's going to be an irrational number, actually, which is interesting to think about. But we'll move on with the theorem. So a squared plus b squared equals c squared. Okay, and of course, originally this would be done all using geometry, right, where we're actually squaring these legs and then adding that area together for the area of the third leg, because algebra hadn't even been invented yet, right? That's not for another several thousand years. So with a squared plus b squared equals c squared, we will first grab our legs, which we can count. 1, 2, 3. 1, 2, 3. I'm counting the spaces. 1 space, 2 space, 3 spaces. They happen to be the same length here. So a is 3 squared, and b, I'm making a mess of things. B is 3, and we're finding our missing variable. Okay. So 3 squared plus 3 squared equals c squared. We've got 3 squared is 9, plus 9 equals c squared, and we have 18 equals c squared. We're not done yet, right? Hopefully you can see 18 does not fit in that little space right there for that triangle. We have to inverse operation, which is taking the square root of a squared variable. Okay, those cancel, and the square root of 18, right? What multiplied by itself is 18? Well, 4 times 4 is 16. 5 times 5 is 25, so it's going to be 4 and some change. And we'll go over to Desmos real quick. I had that typed in a second ago. 4.2 will satisfy. That'll be to the 10th place. Okay? So moving on, this next one, very similar setup. Again, one thing to point out, our scale of these graphs, these are going by ones. You always want to check that when you're counting on a graph. That's 2 spaces, 3 spaces, and so we have 2 squared plus 3 squared equals c squared. Okay, so you'll get a chance to practice in a little bit, but of course if your instructor wants you to practice now or see if you can solve this, then they can hit pause at any time. Rather than solving this, the good old-fashioned way, we're going to plug this into Desmos. I realize these are very easy numbers to work with, but I want to make sure you know this trick as well for solving equations. Okay, so for solving equations, we're going to what I call the y equals trick. We're going to have Desmos draw two expressions, but as lines, so turn them into equations, where we type in y equals the left side of the equation, which is 2 squared plus 3 squared. Okay, that is not our answer. And then we're going to come over here and type in y equals, you can say x squared, but c squared will work as well. Okay, the variable we're searching for. And then the answer is going to be positive, right? But it's going to be where the lines cross, right? The intersection of the lines. So our answer is 3.6. 3.6 equals c. Okay, so that is the distance between L and N. All right, so moving on. Slope. What is the slope of our line segment AC? Well, we can use rise over run, and we'll do that first, right? And so first thing to look at is this a positive slope or a negative slope? The way my brain always remembers this is, we read, right? At least in English, we read from left to right, okay? And so if you just can't remember, write your name, right? Write something, write a word, dog. If you're writing up the page, you're going positive, you're going up. If you're writing down the page, you're going negative, it's going down. So this is a positive slope, so keep that in the back of your head. And then we are going to go ahead and just rise over run. Okay, so our rise, we'll do first, 1, 2, 3, goes on top. And our run, right, we have 1, 2, 3, goes on bottom. And so we have a slope of 3 over 3, which reduces to 1 over 1, or a slope of 1. Okay, and of course I kind of counted that back. You could count 1, 1. There's a slope of 1. We're getting from our point, our intersection point, to an intersection point on our line. Okay, so this is a slope of 1. Very simple problem. All right, now number 4, what is the rate of change? That language, of course, rate of change, you'll see quite often that is equivalent to slope, right? What is the slope of this line? Okay, so again, if you want to write your name on it, writing down the page, write an animal, writing down the page. So it's negative. I'm going to go ahead and put a negative sign there so I don't forget. And then we're going to, instead of counting rise over run this time, because sometimes these get a little tricky, sometimes the scale of the graph is off, I'm going to go ahead and show you how we do that in Desmos as well. And let me pull that up. So this will be a little bit more involved, but again, it'll help for those more complicated problems. We're going to make a table and just take these 2 points they give us from our line here. So we've got 2 and 5, 2, 5, that first ordered pair on top, and we've got 4, 2, 4, 2. Okay, and then we're going to use our equation we learned, y equals mx plus b, but we're going to type it in, Desmos lingo, y1 tilde mx1 plus b. Okay, and there's our answer, right, down here. Slope is negative 1.5. It gives you the slope, and it gives you the y-intercept. So when we're doing our next one, or if you just have to create an equation, I call that the equation builder. So if we're building equations, right, we get some points, some data points, rather if they're from a table they give us, or if they're from a graph they give us, and then we use our equation builder, y1 tilde mx1 plus b, to find the 2 things you need for slope-intercept form, the slope and the intercept. Negative 1.5 is our answer. That is equal to m, which is slope. All right, halfway done. Let's keep going. So our y-intercept. What is the y-intercept of the line that goes through points A and C? So this is kind of a funny question because there is no y-intercept if that's as far as the line goes. We're going to assume the line extends, right? And given that it has a slope of 1 over 1, we could count, we'll do this one this way. The y-intercept is 0, right? And that's really all there is to it. The y-intercept is, of course, our y-axis. You can think of like interception being, like in football, the interception happens when the ball comes in contact with the opposing team, right? It's that interception of coming in contact with, and so the line intercepts with the y-axis, and the y is right there, so it comes in contact right at 0, 0, the origin. Okay, and looking at number 6, maybe a little less clear where the y-intercept would be. Of course, if you had a ruler, that would for these simple problems, but you'll get more complex problems on the STAAR test, obviously, and so we're going to use Desmos to solve this one, which I think these are in the same points. They are in the same points, and so that's lucky for us because we already have Desmos open for us. 2 and 5 would be our L value, right? Our N value is 4 and 2. And you'll notice, right, and that's one of the nice things about these equations, even though we were using it to find slope, they already give us our y-intercept as well, which is 8. Okay, checks out, just looking at it, b equals 8. All right, very good. So moving forward, we've got dilations and transformations. Number 7. Right, well, let's talk about, I guess, what a dilation is first. The way, I talk about it in my class, I'm sure your teachers do as well, is we talk about getting our eyes dilated at the eye doctor. And I would go over and turn off all the lights and encourage you to stare deeply into your neighbor's eyes to watch what happens when I turn them on real quick, right? And what you should see is they go from really big, right, letting a lot of light in when the lights are off, to really small, right? And so that transformation, right, that takes place with our eyes. We can also manipulate things on a coordinate grid. So dilations produce similar figures that are not congruent, right? Not congruent, not the same, right? And have the rule SFX, SFY. Translations, reflections, and what is that SF? That's the scale factor. I'm going to write that. Okay, meaning the scale factor times x and the scale factor times y. Okay, and then we have translations, reflections, and rotations that do produce congruent figures. Okay, so we're not going to go over every single transformation. We're going to go over looks like dilations and translations. So number 7 says triangle ABC is dilated by a scale factor of 0.8 with the origin as the center of that dilation to create the triangle. So here's our scale factor, right? And basically what we're doing is we're taking our points, these 3 points, and we're multiplying them by the scale factor of 0.8. So first of all, what is the rule? The rule is the scale factor, 0.8. Sorry, that's not y'all's bill. 0.8, and that's going to be x, right, times our x values, and 0.8 or 0.8, I'm being a little lazy here, times our y values. And that's for every single x value and every single y value. So that would be, for example, let's just do 1 point. Let's take point A. That's at, well, let's do a little more interesting. Let's take point B because they have 2 different numbers. This is at 5 and 2. Okay, so how is B going to be dilated? Well, by 0.8. So you should be thinking to yourself, I'm dilating, I'm making it bigger or smaller. Which is happening on this? Well, this is going to be less than 1. That's a less than symbol. I try to make them look a little more like L's to help people remember. Less than 1, and so it should be getting smaller. This should be a reduction in size. And so 5, 2, it's going to be 0.8 times 5, right? And 0.8 times 2. And what is that? Let's pull up the calculator real quick. Should be 8 times 5 and 0.8 times 2, 0.6, but that's okay. Put it in the calculator. There we go. So you can see, yes, they did get, the point did shrink. So we're at 4 and 1.6, comma 1.6. It's our new value. that would be located 4 and 1.6, about here. Okay, and so if we were drawing this triangle, you know, it would be something akin to this. Okay, where I'm kind of estimating the other 2 points, but it would be shrunk. Okay, and are they congruent? No, they're not congruent. They're similar. Okay, and what I always tell my students, you know, with dilations and transformations and scale factors and finding scale factors, just remember new goes over old. Okay, and so if I had to find the scale factor from this dilation, I would take my new number, which in this case would be 4, and put it over my old number, which in this case is 5. And sure enough, 4 divided by 5 gets us 0.8. Right, I would take my new value and put it over my old value. And that's a way to, you know, the backdoor way to get your scale factor if that's what you're finding. New over old, new over old. Try to remember that. Okay. And then we have one more. Triangle LMN is translated 4 units to the left and 2 units down. Okay, I like to go ahead and draw arrows, left and 2 units down. And if you don't know your left and your right, I can't help you at this point. You're in 8th grade, so sorry. We have triangle LMN prime, right? And this is something else to point out about these transformed figures we're dealing with, is these apostrophes, that prime notation. That lets you know this is the new figure. Right? Prime means the new figure. Okay. So what is the rule? Well, the rule is we're moving to the left and down, and you know, it should be intuitive. Those are subtraction, right, as opposed to the right and up. Okay, and that's just kind of baked into the cake in terms of human experience. Down is negative, left is negative, right? Sorry for you left-handed people, but that's how it is. Not arbitrary. So what is the rule? The rule is our x values are moving down, and they're moving, well, I say down, they're moving more negative, and they're moving negative, right, to the left 4 times. And our y values are moving down 2 times, and so that's our rule, right? And so I'm going to do that with this point m. I'm going to count 4 spaces to the left, 1, 2, 3, 4, 2 spaces down, 1, 2, and so m prime is at 0, 3. M prime is at 0, 3, and you can do that for each of your points and redraw your figure if you were required to. Are triangles LMN and LMN prime congruent? Are they the same? We read that earlier. Yes, they're congruent, right? We're not changing the size or the shape. We're just changing the position. We're not even changing its orientation, which is the direction it's facing, right? We're not spinning it, rotating it, right? We're not flipping it, reflecting it. We're simply shifting it, sliding it, okay? So that will do it for the notes, right? Your assignment, Triangles in 8th grade math mini quiz, has some very similar questions to what we just went over. There's not that many of them, so this shouldn't be a problem for you to knock out real quick. I will have the live stream open if you all do have questions. Yeah, good luck with that. Use Desmos as you like. Oh, I know y'all don't have your laptop, so if your teacher has, you know, Desmos, they can Google Desmos graphing calculator if you need to do any calculations with it. Thanks a lot. Good luck on your tests. And